Hello and welcome to the first video on Lecture 18, which covers the later half of Chapter 24, namely the topics of single slit diffraction, of diffraction gratings, and finally polarization. So in this first video, we're going to discuss single slit diffraction. Our objectives are to understand what happens when coherent light shines on an object with an edge or an aperture. It diffracts, and learn how to understand the diffraction pattern when coherent light passes through a narrow slit. Okay? I'm going to kind of elaborate on that terminology. I remember it being something that confused me when I was a student, and I want to hopefully make it clear to you. Okay? So let's first of all just define diffraction, kind of in a practical sense initially. So diffraction is the phenomenon that a wave, once after passing through an opening or around a corner, will fill in the empty space. So phenomenon of a wave that after passing through an opening, which is a synonym of aperture, or around a corner, will begin to fill in the empty space. This idea that waves diffract is really included in most sketches of waves. The way we draw waves is kind of spreading out from a single point. That often represents the diffraction of waves, the way that they are able to fill in space. On a more technical side, diffraction is based on Huygens' principle that states that the wavefront of any wave is actually composed of an infinite number of wave sources. So after a wave goes around a corner, that wavefront then can act like a bunch of separate sources, which is how it's able to fill in space where the wave hadn't previously existed. So I'm just going to mention that, right? So this phenomenon is based on Huygens' principle that states that a wavefront, one word, is composed of an infinite number of wave sources. Waves can make more waves. So a little picture showing the idea of diffraction would look something like this. So we could have, if I can draw it correctly, we'll have like an opening, and I'd have a wave coming in, shown with a wave front like this. This is what's called a planar wave because it's a bunch of wave fronts that are all planar with each other. Okay, the distance between them would be lambda. You could think of the purple lines as representing the crest. If we're looking at like an aerial view of ocean waves, for example, it would, it's like a very perfect array of ocean waves. It would look something like that. Okay, and then they're going to come to an opening. If we're continuing the ocean analogy, you could think of that as like a jetty. And then what's going to happen then is the waves are going to come in. They're going to only, like a small part can actually pass through the wall, right? Because the rest of this is a solid wall through which none of the waves can pass. They can only reflect. But that small opening will allow for one little portion of the planar wave to come in. But then after that, the wave will no longer be planar because then it will start to spread out. And the idea is because each of these acts like little wave sources. And so then if we think of this wave source coming out like this, right, each of these coming out, then the overall effect of all those waves is a connecting line that is the new wavefront. And then there'd be another new wavefront, and so on. And so that is the diffracted wave on the other side of the opening. So here we have the diffracted wave and the planar wave. Okay? So when we talk about diffraction, other than qualitatively, the time we care about it is with a phenomenon called single slit diffraction. And the reason we care about it isn't because of the diffraction itself, but because of the interference pattern it creates. An interference pattern that in many ways is very similar to the interference pattern of a double slit opening, but with some key differences. Okay? So that means that really, when we talk about single slit diffraction, we don't care about the diffraction. The diffraction is kind of like a misnomer. That's what everyone calls it. Because really what we care about is the interference pattern. Okay? So I'll make a note of that. So single slit diffraction is a topic that relates to the interference pattern created by diffracted waves from the top and bottom of the opening. We'll say of the single slit. So do you see how it's like we call it the single slit diffraction, just like we call it, but we call the other one the Young's double slit interference, right? Kind of pick and choosing, right? So diffraction is actually happening in both cases. Diffraction was the only way that we could really explain double slit interference, but it wasn't really front and center. We could kind of think of them as just the rays, right? If you think of the previous lecture notes, I drew the double slit interference as rays coming in and, for example, meeting at a midpoint between the two openings. Well, in that sense, yeah, I didn't have to think about so much the diffraction, but it was still happening. The waves were diffracting. In fact, the way that they were able to cover the whole screen was because they had the waves that spread out. They had diffracted. Okay? And now another quick aside, what about the terminology? Diffraction, okay, and interference, and then the word that we've been seeing quite a lot of, refraction. So the way I always summarize it is refraction is the bending of light, diffraction is the spreading of light, interference is the superposition of light. Okay? All right, so now let's get into the nitty-gritty of what that interference pattern looks like. Okay, so this is just going to be another formula, another way of thinking about interference, bright spots and dark spots. Okay, so we had the double slit case, and we had to think about how far apart the slits were, and then we had a screen that was a certain distance away. Sometimes we use a small angle approximation, often, and then we were able to find locations of maxima and minima, bright spots and dark spots. And then we saw something really similar with thin film. We had to think about how many reflective phase changes there were and how thick the film was. And then that was able to tell us whether the waves were getting canceled or not. Okay? Whether it was a dark spot or a light spot, or whether the whole film was dark or the whole film was light. Okay? So kind of same thing here, right? This is the third case of interference. Okay? So really there's three cases of interference so far. There'll be a fourth one, but you have to kind of group that together in terms of the material in the chapter. So really this chapter is mostly about interference. With polarization being the other kind of wave property that we'll talk about as the final part of this set of lecture notes, lecture 18. Okay, but before I get ahead of myself, let's talk about that nitty gritty. So I included this image. This is from hyperphysics.com, great website, and what it shows is it does a really good job of showing what is meant by single slit diffraction and the resulting interference pattern. Okay, so the idea is that we want to think about two rays in particular. We want to think about the ray at the very top of the opening and the ray at the very bottom of the opening, because those two rays are then going to be able to interfere with each other, okay? And the way they interfere with each other is going to be relevant, because then if we thought of another ray that's slightly below the top one, well, it would interfere with a ray that is going to be slightly above the bottom one, and it would interfere in the same way. So it ends up that we can pair up rays in the upper half and rays in the lower half by just thinking about the one at the very top and the one at the very bottom. Okay? So we have an assumption of an infinite source, distance that gives a planar wave, like the one I drew over here. And so then when it goes through the opening, that wave has no directionality. So then it's diffracted perfectly. Okay. We're also going to think of the distance to the screen as being much, much larger than the opening. So we're always going to be using the parallel ray approximation. And you might think, oh, well, hey, these two rays don't look anything like parallel, do they? Well, that's because we just wanted to draw them all, extending all the way to the screen. So we draw them as not parallel, but the assumption is that we always are assuming that they actually, in fact, are parallel. Okay? So we're using the parallel ray approximation. We will not always use the small angle approximation, but we will always use the parallel ray. Okay? And if you want to see a time where you don't use the parallel ray approximation, I did go ahead and have next week's post quiz be exactly that. That's going to be the main takeaway. All right. So, okay. Then what's happening here? Well, if you look, we got tangent of theta is y over d. Okay? Well, that's this triangle right here. Okay. Let me choose a brighter color. So that's this triangle. All right. So, and that's exactly tangent of theta. All right. And that's just going to be the distance from the midpoint of the opening right there to, well, some point on the screen. Okay. Simple as that. For the small angle approximation, we can say that tangent theta approximately equals sine theta, approximately equals theta. In that case, would approximately equal y over d. Okay, so that's something we can make some of the time. Now, what are the conditions for a minimum? Well, for the minimum, we need to make sure that the waves arrive exactly out of phase, right? Because that's the only way you're going to get a dark spot. And to arrive exactly out of phase, you have to make sure that they have a half wavelength difference. Okay? When we look here, it says that the condition for the minimum is the thickness times sine theta equals the order, so just some integer m, times the wavelength. Well, where's the 1/2, right? Well, it comes from the fact that the 1/2 we're looking for 1/2 lambda, but we're also looking for 1/2 the opening, right? Because remember, we're comparing waves in the upper half to wave rays, really, rays in the upper half of the opening to rays in the lower half of the opening. Think about every one of these little black lines as being a source of a ray, right? And so since we're comparing 1/2 of the opening to 1/2 of a wavelength, when you often see the condition for a minimum, the 1/2s have already been canceled for you. And in fact, that's going to be the way it's presented, okay? And so then what we really care about, what we're going to be using, is just that the width of the opening times sine theta equals m times lambda as the condition for a dark spot, okay? So for the small angle approximation, that simplifies to simply that y equals approximately m lambda d over a, okay? So down here in the formula, which we kind of already started talking about, I'll label everything, make sure it's all clearly labeled. Y is just the distance from the center so the distance of from the center of the screen to the location to, some location, okay? This is just distance from, and actually it's not just some location, it's to the mth bright spot. So distance from center to mth bright spot, okay? And that's on the screen. You can see that y is clearly labeled in the figure. M is just the order of the bright spot. Oh, sorry, dark spot. I make that mistake because obviously we talk about the formula that we use for double slit interference is we count bright spots. In this case, we count dark spots. The reason for that is a bit beyond the scope of the class, but it's basically because the approximation works a lot better for the dark spots. This has more approximations built into it than the double slit interference. So that's why it's more accurate. So, and the dark spot. All right, and then so this is the, mth order of dark spot. All right, and then that's going to be m equals 1, 2, 3, etc. So notice it doesn't include 0. That's just like with the double slit interference. We didn't count with 0. In fact, the only time that we have these sort of counting equations that involves 0 is with a thin film. So it's always good to remember that's the exception. D is just the distance from the slit to the screen. All right, and then A is the width of the slit. All right, and obviously M is the wavelength. Okay, this is dimensionless because it's meters over meters times an integer. All right, and then the way the formula is written is that this is always true. So you could always say that sine theta equals m lambda over A. And sometimes you can say that sine theta is just equal to y over d, in which case you don't have to even worry about the angle, and then you can just use this part of the equation. Okay, that's when you're using the small angle approximation. So actually go ahead and kind of highlight that. So this would be for small angle approximation. Okay, so I guess we are good to go and look at some examples, which I'll include in this video. So in the next video, we can talk about diffraction gratings. All right, so what example do we want to take a look at? So let's flip to the next page. All right, and you can see we have our practice here. All right. So first one I think is a good, interesting one. Kind of think about maybe sometime you might actually use this stuff. All right, and that would be making the measurement, right? Trying to make a really small measurement. So you asked to measure the width of a tiny rectangular opening in a circuit board, but realize that your calipers are the things for measuring distances, are not precise enough, right? Because it's a tiny opening. Instead, right, clever workaround, you shine a green laser with a known wavelength, probably maybe print it on the side of the laser, through the opening, and then carefully align a whiteboard parallel to the opening at a distance of 3 meters away, right? So it's nice and far away so that then when the interference pattern is seen on the whiteboard, you'll have nice, easily measurable distances. So with the diffraction pattern on the board, you measure the distance between the two minima on either side of the central maxima as 10 centimeters. What is the width of the rectangular opening? Okay? So let's think about how we do that. So first of all, can we use the small angle approximation here? Okay, so check for small angle. All right, so I'm just going to find tangent theta. So I'm going to say that theta is, tangent inverse, and that's just going to be y over d. We know we want to measure a distance of 10 centimeters. So then I'm going to have tangent inverse of, or in fact, that's what we do measure, divided by 3 meters. Let's see what we get. As long as this is less than 12 degrees or less than 15 degrees, then we're going to be in good shape to continue with the small angle approximation. All right, and indeed it's 1.9 degrees, so we are fine. All right, so which tells us we have a small angle. Okay, so how do we proceed from there? Well, then we can just use the formula that doesn't have the sign in it. So we'll just use y over d equals m lambda over a, and we're trying to solve for a, right? Because that's our unknown opening size or width. Okay, so if I do that, then I'm going to have m, well, which m, right? Well, I'm told that I'm looking at the distance between the two minima on either side of the central maxima. Okay, well, let's look at the picture here, right? So there is something different about the diffraction pattern of the single slit, right? Because before, with the double slit, we had a bright spot that was exactly halfway between the two slits, right? That was our central bright spot. And that bright spot had a width that was the same as any other bright spot, right? The pattern was totally symmetric. Well, here the pattern is totally symmetric relative to this midline, right? So if I go in this direction, there's symmetry. But the one thing that is asymmetric about the single slit diffraction pattern or interference pattern is that the central maxima is twice as wide as any of the other maximas, okay? And so in other words, the distance between the midpoint and the first minimum is the same as the distance between any two minimum. But the distance between the two first minimums is twice as far as the distance between any subsequent minima. Okay? So it's a good thing to think about. And it's really because the central bright spot of the single slit pattern is kind of like two bright spots that are fused into one. And so its effect is that it is twice as wide, right? And its intensity is really high. The kind of the way that the curve is drawn here with the central one being so much higher is also true. It's when we actually calculate the effect of the intensity, it's much more dramatic in the middle, whereas the double slit pattern has the biggest peak in its middle, but it's not quite as big relatively. The other thing to think about, which we won't, is kind of the overlay of single slit and double slit effects, because they coexist, right? Because if you think about a double slit, well, the double slit is acting like two single slits and a double slit, and the interference pattern is a combination of all three. In effect, we usually think of it as a combination of just one of the single slits, because it turns out that the formula that we get for single slit interference, because we're dividing by A, and because A is the width of the opening, and that formula is so similar to the formula for the double slit, where we divide by D, which is the distance between the openings. Well, think about it. If we're dividing by a much smaller number for the formula for the single slit interference, that tells us that the spacing of the single slit interference is way wider than the spacing of the double slit interference. So when you look at an actual interference pattern, you're seeing both effects. And the effect that's really fine is the double slit interference, and the effect that's really big and spread out over many centimeters or meters is the single slit interference pattern. Which is kind of counterintuitive. A lot of people think it's the other way around, but until they check the numbers, right? But I'd say looking at the formula really gives that away, because of course dividing by a small a gives you a large y. All right, back to the problem. So let's plug in our numbers. So we have an m equals 1. All right, so I have 1 right there. And then my lambda, which was given as 570 nanometers. Okay. And then I would multiply by d, because they are cross multiplied, right? Like so. And so if I'm multiplying by d, that's going to give me 3 meters. All right, and then I'm going to divide everything by y, which we know to be 10 centimeters. All right, and let's think. Yeah, I want to make sure though, because I'm what we're looking at. So we're told that it's 10. Yeah, oh, this is relevant to what I just said. So it says you measure the distance between the two minima on either side of the central maxima, right? So that distance right there is twice as far as y to the first minimum. So the y is measured from the midline, the middle of the central bright spot, to the first minimum. So if I'm measuring the distance between those two, it would be twice that. So for an m of 1, I have to actually put in 5 centimeters. Okay, because it has to be half the value. It's simply this, right? I'm simply, not to overthink it, right? I'm just looking at this value, which is half of this value. And this value was given, or the longer value was given as 10 centimeters, and I'm interested in the shorter value, which is exactly 1/2 of that. Okay, so let's get the answer. And it ends up being 34 microns. Okay. So that is our A. All right. Good. So 34 times 10 to the negative 6 meters, which would be 34 micrometers, also known as 34 microns. All right, so which one do we want to look at next? So I'll leave example 2 for practice. It's pretty straightforward, just kind of continuing with the same idea. I'd say let's do a concept question for sure. And then we'll do one more example, and then we'll wrap up this video. All right, so in this concept question, it says the diagram shows a single slit with the direction to point P on a distant screen, right? So clearly showing the parallel ray approximation. At P, the pattern has a maximum nearest the central maximum, okay? So here we actually are talking about a maximum, which is fine, we can. And we can assume that they're about halfway between every minimum, right? It's a rough approximation, but it's close enough. If x and y are the edges of the slit, what is the path length difference px minus py, right? So how could we find the difference in order to get that constructive interference? Okay. So the idea then is this. So we simply reason this out, okay? So we know the first order maximum has a phase difference of 3 pi. Okay, so how do we know that? Well, let's think about what's happening here. The center of the central maximum has a phase difference of nothing, right? So the rays are in phase. If we want to have constructive interference, the next point that we can have constructive interference would be a phase difference of 1.5 wavelengths. Okay, because only then are they going to be only then will they arrive in phase. Okay, so we have because we're asked if x and y on the edges of the slit, what is the pathing difference px minus py? Okay, so point P, the pattern has its maximum nearest the central maximum. Okay, so let's see, because we need them to travel. But I do need them to be in phase when they get there. So let's think. So yeah, I think that, I'm not sure why I wrote 2 pi. Yeah, I'm just going to correct this. So, because 3 pi doesn't make sense because then they're going to be out of phase. They'll have the half wavelength out of phase. So the idea here is that they would have a pathing difference of 2 pi, which is going to be one wavelength. So, sorry for the confusion, but quickly corrected it. Thus, the path length difference is lambda, right? Because then they will arrive in phase. They're exactly the difference in the path they take is exactly 1 wavelength, and that will give us our first bright spot. Okay? All right, so let's look at our final quantitative example here. Okay. So, what are we interested in? Okay, so we have visible light of wavelength 550 nanometers. Oh, I thought I corrected the typo here. But just formatting error, you can see. Falls on a single slit and produces its second diffraction minima at an angle of 45 degrees, right? All that jargon is just formatting that was supposed to be deleted. So we can just get rid of this. So it should just say at 45 degrees. Okay, and 45 degrees is definitely not a small angle. So right away we know we're not going to be using small angle approximation. Just by that number being stated, we know immediately. Okay, and then it says what is the width of the slit and at what angle is the first minimum produced? Okay, so we should be able to just jump into using the formula. So we know we're going to have sine of theta, and here, I'm referring to this one here, right? We know we're going to have sine of theta equals m lambda over a, okay? So equals m lambda over the width, okay? Do we have all the information? Well, yeah, we actually do, right? Because we're trying to solve for a. We know that m is the second minimum, so it's an m of 2. And we know theta is 45 degrees. Okay, so let's go ahead and solve that. So then a is just going to be 2 lambda divided by sine theta, which will be 2 times 550 times 10 to the negative 9 meters, all divided by sine of 45 degrees. Okay. Plug in the numbers. Okay, so we get 1.56 microns. Very good. Okay, nice, very small slit, right? So then, what if we want to find the first order one? Well, that should then just be a matter of plugging in m equals 1 with a known a and solving for theta. So now solve for theta, okay, from the same equation. And so then it's going to be theta equals sine inverse of, I'll say with m equals 1. Okay, because it's the first order dark spot. All right. 550 times 10 to the negative 9 meters, and then divided by the value that we just solved for, by our width. That'll work. 1.56 times 10 to the negative 6 meters. All right. I'll take the unrounded value of my calculator. So sine inverse 550 times 10 to the negative 9 and divided by 1.56 times 10 to the negative 6 gives me 20.71 degrees. All right. Or let's see, we're really working with 3 sig figs, so 20.7. There you have it. So that's kind of cool, right? Not using a small angle approximation and working backwards to find the final location like that. All right. So, and the whole reason we didn't use the small angle here is because obviously the screen was, was close, at least close enough that the spread mattered, right? Really